So this presentation is going to be about Boolean algebra. So Boolean algebra, invented by George Boole, was sort of an algebraic system, a series of rules, theorems, let's call them, which are true because we know that the only possibilities are 0 and 1. If we had to consider other cases here, this wouldn't be true anymore. But because they're only 0 and 1, there's a bunch of rules that we can use to help simplify, a bunch of theorems. So we're going to go through all the theorems and do some practice on simplifying some expressions based on those theorems. The first four theorems are the AND gate theorems. Now, throughout all these, we need to be careful that some of these things, we're going to get very comfortable, some of them feel just like regular algebra, but you can't assume that just because something works in regular algebra means that will work in Boolean algebra. So let's start here. The first theorem says x, so any input, if it's ANDed with a 0, is a 0. So that should make sense. If you have 0 and 0 on an AND gate, you know the output's going to be 0, or 0 and 1, or 1 and 0. If you have any zeros in there, the output's going to be a 0. So anytime we see something ANDed with a 0, we can just presume that it's going to be a 0. So that's the first theorem. The second theorem says that anything ANDed with a 1 is itself. So if you think about the truth table for an AND gate, you've got 0, 0. Well, that's not in this case. We don't worry about that. You've got 0 and a 1. If you had a 0 and a 1, the output would be a 0. So if this is a 1 here, the x is a 0, then the output's a 0. It's itself there. And then if I have a 1 and a 0, well, we're not talking about that case either. We're only talking about cases where x is ANDed with a 1. And here's the other possibility. If x is a 1 and it's ANDed with the 1, well, then the output is a 1. So what George Boole noticed is he said, in this case here, if it's ANDed with a 1, if there's a 1 in the column here, and it happens to be a 0, the output's a 0, and it happens to be a 1, the output's a 1. So if that's the case, anything ANDed with a 1 is itself. So again, that just helps us to simplify. He also noticed that anytime anything was ANDed with itself, it was itself again. Because if I look at the truth table, 0, 0 on an AND gate, the output is 0. And 1, 1 on an AND gate, the output is a 1. So really, if they're the same, it's just itself. Anything ANDed with itself is itself. My last theorem here says that anything ANDed with its inverse, here is a 0. And the only times I can have that is 0, 1 and 1, 0 on an AND gate. 0, 0 and 1, 1 don't count. So if I've got 0, 1 and 1, 0, both of those on an AND gate result in a 0. So George Boole noticed, well, if that's the case, then these have to be 0. So anything ANDed with its inverse is a 0. Okay, so this one sort of makes sense with regular algebra. Anything times 0 is a 0, that's true. Anything times 1 is itself, that's true. But over here, not so true anymore. Anything ANDed with itself, anything multiplied by itself is not just itself, right? It would be that squared. We don't see that here. And anything multiplied by its inverse is a 0. That certainly doesn't make any sense either. So these ones are very specific to Boolean algebra. Now let's look at the second set of theorems. These are the first four AND gate theorems. Now we're going to look at OR gate theorems. Now that we're looking at theorem 5 through 8, you'll notice I left 1 through 4 up there because they're dangerously similar. It's really important to make sure that we're looking at both of these so we can see there's some similarities, but there's also some pretty important differences. So theorem 5 through 8 are the OR gate theorems. And so here we see x plus 0 is itself. So if I think anything ORed with a 0 is itself. Okay, so my combinations, my possibilities are 0, 0 and 1, 0. On an OR gate, 0, 0 would in fact give me a 0, that's true. And a 1 and a 0 would give me a 1, because in an OR gate, if either input is a 1, then the output is 1. So that makes sense. Whatever is in this first column here, that's what the output is if it's ORed with a 0. Moving on to theorem 6 here, anything ORed with a 1 is a 1. Well, that's kind of the cool thing about an OR gate. is that if either or both of the inputs are a 1, so if I've got 0, 1, or I've got 1, 0, or I've got 1, 1, in all of those cases, the output is a 1. So here we're talking about this case, and we're talking about this case. Anything ORed with a 1 is a 1. Theorem 7, anything ORed with itself is itself. That looks a whole lot like Theorem 3 up there. Those are pretty similar. So again, my possibilities are 0, 0, and 1, 1. And on an OR gate, 0, 0 gives me a 0 output, and 1, 1 gives me a 1 output. So sure, anything ORed with itself is itself. Theorem 8 says anything ORed with its inverse is a 1. So my possibilities are 0, 1, and 1, 0. And on an OR gate, both of those give me a 1. So if there's an inverse involved, I know it's going to be an output of a 1. Now, be careful, because look at Theorem 4 and Theorem 8. They're set up the exact same way. Something ANDed with its inverse, something ORed with its inverse, but the outputs are completely opposite, right? Totally different. Same thing over here. Anything ANDed with a 1 is itself, but anything ORed with a 1 is a 1. So you just got to be really careful. Use this as a crutch. Have the theorems nearby, have them on a wall, have them in your notes, so that you can constantly verify. When you think you can make a simplification, double check. Is that Theorem 8 that said that? Oh yeah, here it is. Now I know it's true. Theorem 9 is a pretty obvious one, but it comes up really often, so it's important to talk about. And Theorem 9 says that anything double inverted is itself, which makes sense, right? If x was a 0 and you invert it once, it becomes a 1, and you invert it again, it becomes a 0 again, right? So anything double inverted is itself. If you thought about the actual circuit there, that would be an inverter and an inverter. Now this seems kind of silly at face value, like why, of course, right? Why would anybody double invert something? But as we go through the process of simplifying, you'll actually find that this happens really frequently. We'll see double inversions or quadruple inversions or triple inversions. They're going to come up pretty often. So it's important to know that I can just get rid of both of those inversions. And in the circuit, I would actually just be able to eliminate both of those, and it would just be x. So that's Theorem 9. Theorem 11 through 16 I'm going to go through pretty quickly because they're theorems that we're pretty familiar with from standard algebra. The first is what we usually call the commutative law, or what I like to call the order doesn't matter law. So what we see here is that x and y is the same as y and x. The order doesn't really matter there. And same thing with the or. X or y is the same as y or x. So we're allowed to move those things around. The order is irrelevant. We will have to think about, as we get things ANDed and ORed in the same spot, we will have to think about order of operations, which we stick to. But as long as we're doing all multiplying or all adding, any kind of change around in this order doesn't matter. Theorem 13 and 14 are typically called the Associative Law in standard algebra. And basically that's saying that x times the quantity yz is the same as the quantity xy times z. So these parentheses, since we're just doing all this multiplication here, parentheses don't really matter where they are, in this case, if they even exist. Down here, same thing. I can put parentheses on these if I want to for ease of visual, but the order doesn't really matter, or where the parentheses is doesn't really matter for a situation like this. Theorem 15 and 16 are the distributive law that you normally see in algebra. And that's probably one that you're going to be using a lot. And we see here that x times the quantity yz would be equivalent to xy plus xz. And you see we would call that like distributing out there. And here, same thing. We might see some distribution here. When I was in school, we were told the FOIL method, first, outer, inner, last. I know some people do like pairing or bracketing. So whatever you're familiar with, you're comfortable with. But here they did x times w, so xw is over here. Then xz, the outers, that goes there. Inners, y times w, that goes there. And then the last, y times z. And so this and that are equivalent. And a lot of times we're going to want to do that to set up other types of simplification. But we know that that is true for Boolean algebra as well. So the consensus theorems are the next ones, and they tend to be the trickiest ones to see. The way I like to explain this, if you've ever seen the movie Jurassic Park, there's a situation where Muldoon, who's the hunter guy, is talking about the raptors. And he says that what happens is you're looking one dead in the eye, and you made contact with it, but that's when the other one attacks you from the right side. You never knew were there. And he says, "Clever girl," in his Australian accent. And then it attacks him and everything. So that's what I always say the consensus theorem is. You never really know. You think, I can't get any more simple. This is as simple as it gets. And then that's when that consensus theorem sneaks up on you. So I call it the raptor. That's my raptor. So let's talk about the consensus theorem real quick. And here they are. What you're mostly looking for with the consensus theorem is some variable and its inverse, its order that's inverse and something else. So, for example, here I've got x and its inverse with a y. Here I've got x and its inverse with a y naught, x naught and its inverse with a y, x naught and its inverse with a y naught. So that's the form you're looking for. Something ordered with its inverse and another variable. And what you'll notice here, and this is kind of a nice little shortcut, is if you can get it into this format, you can move things around via the associative property and the commutative law. If you can move them around into this format, the answer, the simplification, will be the outside two terms. It's a little shortcut. So here I see with theorem 16, it's actually xy. And here it's x, y naught. And here it's x naught, y. And here it's x naught, y naught. And you can see that's the final form of all of these. X or y naught, x naught or y, x naught or y naught. So when you're trying to simplify and you think you've got it down as far as it goes and you think you can't get any further, it's probably one of the consensus theorems, 16 through 19. That's that raptor that's going to come get you. Before we talk about Demorgans' theorem, which is the last few, let's try some practice problems so we can see how our understanding is. So here we go. Let's start with A, B1 plus B, C, C. Yeah, that's good. Let's start with that. So there are some different tactics you can take. It doesn't really matter what order you do them in. As long as you stick to the rules and the theorems, you'll be fine. So the first thing I would look at this and I'd say, well, what can I do with this? And then whenever I see numbers, a 1 or a 0, that usually means there's a theorem I can use. So here I have something ANDed with a 1. So if I look back to my theorems, I'll just leave those over there. I see that anything ANDed with a 1 is itself over here in theorem 2. So what I'm going to do is I'm going to rewrite this then, A, B, because anything ANDed with a 1 is itself, plus B, C, C. And then what I'm going to do is I'm going to write theorem number 2 over there, so I remember how I made that change. So a little bit like geometric proofs if you've ever done that. Next thing I would probably do is I'd look at these two C's over here. I see those two C's, that seems a little strange. So down in my theorems again, I see, okay, so anything ANDed with itself is itself. Well, in that case, BCC is just going to become BC. So AB plus BC, and over here I would write that's because of theorem number 3. Is there anything else I can do here? Well, some of you might think, well, the distributive law says that I can take B out of that, and I'd be left with A plus C because of theorem 14. And that's true. You could do that. But the problem would be that you are, in that case, creating a POS expression. And that's not what we're trying to do. Remember that we want to keep things in SOP, sum of products. So in that case, we probably would have ended with this right here. That would have been the correct answer, the most simplified form. Now, what's interesting is up here, I would have had 1, 2 AND gates, 4 AND gates, and an OR gate. So this circuit right here would have had 5 gates. This one down here, 1 AND gate, 2 AND gates, and an OR gate. I cut 2 gates out of it with just a real simple piece of Boolean. Let's try another one. All right, so we've got some more terms to deal with here. I like to, before we try and distribute, because it seems like people tend to distribute pretty often, I like to see if there's anything else we can do. In this case, it doesn't really look like there's much we can do before we distribute. So it looks like we're going to have to go ahead and distribute. So I'm going to start this guy over here, m naught q plus. All right, so we're going to do first, outer, inner, last. So I've got m naught plus m q plus m naught w naught plus w naught q. Okay, so that is because of Theorem 14, or 15, depending on which. It's probably better to be 15. All right, so what can I do with this? Well, I'm going to need my theorems back here. Pow, there they are. So I've got a lot of different things I can look at over here, but I'm going to start with m naught. That looks pretty suspicious right there. Something ANDed with its inverse. So if I peek down here in my AND theorems, I see, okay, something ANDed with its inverse is a 0. So we're going to go ahead and we're going to replace m naught with a 0, and that's because of Theorem 4. So I'm going to bring everything back down. I'm not going to skip any steps here. There we go. Now, what should I do with that 0? That also looks pretty suspicious. What do I do when something is ORed with a 0? So I look into my OR theorems and I say something ORed with a 0 is itself. Now be careful. You just think, well, I can just plus, anything added with a 0, I can just get rid of it. Well, why? Because of this theorem. Make sure you're spelling that out. So m naught q plus, I've gotten rid of that, mq plus m naught w naught plus w naught q, and that was because of Theorem number 5. Now I'm going to get rid of these parentheses. The parentheses aren't really doing anything for me right now, and that has to do with the Associative Law, right? The Associative Law says those parentheses don't really mean much when I've got an addition sign before them. So I'm going to go ahead and I'm going to get rid of that. M naught q plus mq plus m naught w naught plus w naught q because of Theorem 13. Now what? Well, I think I'm going to take the q out of these two guys right here. See those two? And I think there's something I can do with that. So I think I'm going to take a q out of both of those terms and see what that leaves me with. So I'm going to take q, and that leaves me with m naught plus m plus m naught w naught. Looks like a v. I better fix that. W naught plus w naught q. And that I can do because of Theorem 14, distributive. Well, now what? M naught plus m, something ORed with its inverse. I think that's a theorem. Let me look down here. And, oh yeah, there it is. Anything ORed with its inverse is a 1. Cool. So really, that's q times 1, ANDed with a 1, plus m naught w naught plus w naught q. And that was because of Theorem number 8. Let's see what else we can do. Anything ANDed with a 1, that sounds like a theorem. Anything ANDed with a 1 is itself. Yep. Anything ANDed with a 1 is itself because of Theorem number 2. So that's just going to be q plus m naught w naught plus w naught q. Theorem number 2. I'm running a little out of space here, so I'm going to get a fresh sheet and move this up to the top. So I just moved that right where I was. I moved to the top here so we can keep going. So I've got Q plus M naught W naught plus W naught Q. What can I do with that? Well, I'm looking again probably at some distribution here, at some factoring. So I see this Q by himself, I see a Q over there. So I'm going to take Q out of both of those two terms. So let's see, that gives me Q times. Well, if I take Q out of here, I'm left with W naught. So I'm going to put that in, W naught. What happens if I take Q out of Q? Well, Q divided by Q, anything divided by itself, is a 1, just like in standard algebra. So if I take Q out of both those terms, I'm left with W naught plus 1. And I can't forget to bring the rest of my expression down. All right, and that's true. I'm allowed to do that because of the distributive law. So that's number 14 again. Okay, well, something ORed with a 1, that sounds like a theorem. We look down here, anything ORed with a 1 is a 1. Okay, well, that's pretty handy. So anything ORed with a 1 is a 1. So that's going to be a 1. And that was because of theorem number 6. Getting pretty darn simple here. But I think we can keep going. I got Q ANDed with a 1 here. So let's see. Anything ANDed with a 1 is itself. So Q ANDed with 1 can just become Q plus M naught W naught because of theorem number 2. I think that's about as simple as we can make it. Q plus M naught W naught. So again, if we analyze this real quick, that's 1 OR gate, 1 AND gate, and 2 inverters. So about 4 gates. If I look at my original, there it is. I'm looking at 1 inverter, an AND gate, an OR gate, another OR gate, 1, 2, 3, 4, an inverter 5, an AND gate 6, another inverter 7, an OR gate 8. So we're looking at 8 gates down to 4 gates. That's a pretty impressive shift. Plus quite a bit less wiring over here too. So this is a pretty great simplification. Cool. Let's try another one. Okay. So what have we here? What you might think that you'll want to do is take L out of these first two terms. And you can do that, and you're left with M N plus M naught N naught. And you think back to your theorems. And you say to yourself, this is something order that's inverse, right? So that would be like theorem 8. And that's where you'd make your mistake. This, what you see here, is not the same as that. Those two are not equivalent. It's really important that you see that difference. This is M naught and N naught, where this is Mn naught. If I were to draw that circuit, it might make it a little more obvious. The top one is M naught, N naught, M, N. Whereas this bottom one would be an AND gate, Mn, with a knot after it, a single knot after it. Not only are the circuits different, but the answers would be different. You'd get different things out of them. So it's important to understand that those are not the same thing. You cannot use theorem number 8 on that guy up there. So we're going to have to take a different tactic. So if I can't take the L out of those two, if that doesn't help me, I'm going to look at this other guy over here, this. So if I take Ln out of these two terms, let's see what I'm left with. Ln, I'd be left with M plus 1. Bring the rest of my term down here. L, M naught, N naught. That's because of the distributive property. I'm allowed to do that, so I'll put that out there. And m plus 1, that's a theorem down here, right? M plus 1, that's number 6, and anything ordered with a 1 is a 1. So that's actually just going to be a 1. Ln ANDed with a 1. Oops. And that's because of Theorem 6. Now anything ANDed with a 1, anything ANDed with a 1 is itself because of Theorem 2. So Ln just becomes that. So Theorem 2. Okay, well if I can't take n out of those two terms, because there's no n over here. I can't take m out, so I have to take L. There's really nothing else I can do. So let me take L out of here. I'm left with n plus m not n. Not. And that's because of Theorem 14. Well, now what do I do? There's nothing really to factor. This doesn't look like it's any of my theorems. I guess I'm done. Oh, no, of course. It's the raptor. That's the one you didn't see coming. Yeah, it's a consensus theorem. It's the consensus. It's not quite in the order we expected it, but it is the consensus theorem. I'm going to rearrange the order so it looks a little bit more like what we expect. So, n plus n naught m naught. That's a consensus theorem. Let me zoom in a little bit down here. See which one that matches. Well, this is like the x, so it's really like x plus x naught. So x plus x naught, y naught, that's that one. It's number 18 there. So that gives me x plus y naught. So up here it would give me n plus m naught. So we'll go ahead and we'll put that in. L n plus m naught. And that's because of consensus theorem number 18. Now this looks pretty simple, but I actually probably shouldn't leave it like this because again, this is in product of sums form, and I don't really want to keep it in product of sums form. I want to be in sum of products. So what I'm going to do is I'm going to distribute that back in. I'm going to say this is really Ln plus Lm naught because of theorem 15. Demorgans theorems are on a separate PowerPoint with Project Lead the Way, but they're so similar I'm just going to go ahead and discuss them really quickly here. And it kind of comes back to that idea that Mn, with both of them knotted, is not the same as Mn, like that. Those are not the same. What Augustus de Morgan found out, oddly though, is that M naught, N naught is the same as M or N naught. So when he changed the sign, they actually were equivalent. These two will be an equivalent circuit. Also, M plus N, both knotted, is the same as Mn naught. Those things are the same. You can actually go through and you can look at the circuit, you can look at the truth table, and you'll find that if you have an AND, but the two inputs are knotted, it's the same as an OR with a NOT after the gate. Same thing down here. An OR gate with both inputs knotted is the same as an AND gate with an inverter after it. Okay? So what we found, not we, I wasn't there, but this is a nice little mnemonic here, is to say that when we want to do De Morgans, when we see this sort of thing going on, we're going to break the line and we're going to change the sign. Break the line, change the sign. Makes me feel like Jesse Jackson Jr. Break the line, change the sign. So whenever I see a knot over more than one term like this, and I want to split it apart, I'm going to break the line, I'm going to change the sign. Because it's really hard to do other Boolean theorems if things are under a double, knot like this. It's hard to get in there and work on it. So you usually want to break these lines whenever you can. They almost act like parentheses. You want to break them whenever you can to get in a little bit further. So let's look at an example of that. So here we have a situation where we've got a bar going across this whole big thing here. So we're going to break the line, we're going to change the sign. But the question is, where do we break the line? So typically, you can only break the line at equal spots. So here they're in parentheses. So we can't break these lines here and change these signs yet. We can't do that. You can only do it here at kind of this top level. So we're going to break the line there, and we're going to change the sign. So the sign here was multiply, right? So we're going to be able to change the sign to plus. So this quantity j plus k naught plus L naught plus m. Now, do not forget, real common mistake, don't forget to still have these lines. They're still there. You just got to break it. You didn't get to delete it. So it's certainly still there. All right. Now, we can start to look inside the parentheses, because these bars are just over the parentheses. So I can break the line, and I can change the sign here. So break the line, change the sign. J plus k becomes j times k naught. And again, the bar is there and there. I broke the line, and I changed the sign. I'm going to do the same thing on this side. It's the exact same idea. Here's L, and now it's going to be times M. It's a little more like a minus. Times M. And there we go. So now what? Well, Theorem 9 that we talked about tells us that with double inversions, double bars, we can just get rid of them. The k naught is the same as k. So really this is j naught k plus L m naught. And that brought the circuit down again pretty significantly. Some good simplification right there. Let's do one more. Oh, that's a lot of bars. So it's important again to think about where we're breaking the line and changing the sign. If I break the line here, I really can only change this side. These are under bars. I'm not allowed to get in there and mess with those yet. So really this is the only sign I get to change. So we'll go ahead and we'll break the line and we'll change that first sign. So this is C D naught E bar multiplied by C naught D E naught bar. So I could Demorgans again, but what we find first is double inversions. Good old Theorem 9. That's going to save us some time. So Theorem 9 says those double inversions leave this as C D E C naught D E naught. You'll notice I didn't do any Demorgans there. That was just Theorem 9, so no signs got changed. We just got rid of the double inversions. In the next slideshow, we're going to look at our majority vote circuit. As you recall, that expression was 8 min-terms long, so we're going to go ahead and go from 8 min-terms to about 4. 8 min-terms to 4, and reducing the gates quite a lot. So we'll see that on our next presentation.